So it's a pleasure to have Dr. Mauro Perego giving us a seminar today on his work, and he's a renowned expert in sea ice and ice sheet modeling. So he did his PhD at the Politecnico in Milan, and so he's from Italy, and his work involved at the beginning, discretization and solutions of PDEs, also optimization, UQ, and now machine learning. And so we're really very much looking forward to his presentation, and thank you everybody for attending. Yeah.
Thanks a lot for the invite. It's a pleasure for me to give this talk. So as the title says, I want to walk you through today some of the computational methods that we use in ice sheet model, in particular, when we want to come up with some uncertainty estimates on our predictions. And so we start from the large-scale calibration with Bayesian sense, and then move towards the propagation. The work I'm presenting here is the result of contributions from many collaborators that I listed here, and then different section of the talk I'll mention the main collaborator for each part of the talk later. So this is the outline of the talk. First, I'm going to giving some motivating arguments and the goals of this work. I present the ice sheet model, the equations, and the actual code that we're using. And then I'll talk about the Bayesian inference. This first part I'll talk about the deterministic inversion when you do for doing the Bayesian calibration, and then we wrap this into a Bayesian framework, and in particular we present Gaussian approximation and posterior. And then we sample for this posterior and propagate the uncertainty in our prediction. And we do that, we accelerate this process with a multi-fidelity approach. And we'll give results on the Humboldt Glacier, which is the Humboldt, the glacier in Greenland, on the northwest Greenland that's like there. Most of this work has been sort of been in the literature for a while. The part that's novel and more recent is the multi-fidelity approach, so it's the last part. But I think it's good to walk you through the old process. I think it's starting. So this work is supported mainly by the Office of the Department of Energy, Office of Science. There are a couple of projects in particular. Fancy and Prospect are projects that fund directly the ice sheet work, and then it's coupling with the Earth system model. So the Fancy is the first one is the PI is Matt Hoffman from Los Alamos, and the former project was Prospect by Steve Price, also from Los Alamos National Labs, and then another project funded. This is FastMath, this Oscar project, and the PI is Esmond from Lawrence Berkeley National Lab. So the motivation. So why we are doing this? Why are we interested in ice sheet dynamics? So here I'm showing the some observations of the sea level in like about 25 year spans, started in 1993. This is from I took this from the NOAA website, and essentially you can see in the dark gray line is the observation of the global sea level from satellites, and there are two main contributions to the sea level. One is the added water to the ocean, and this comes from mainly from glaciers and ice sheets. So essentially, when a glacier retreats and loses mass, that mass directly goes into the ocean, essentially, and directly contributes to the sea level. And then the other contribution is the thermal expansion. So as the ocean gets warmer, it expands, and so you occupy a bigger volume, and so the sea level increases. So as you can see, the sum of these two terms is the purple one, and which match very well the observations. And you can probably also can notice that added water term is the major contribution to the sea level, and so that's really motivate our work and why we want to work on ice sheet dynamics to get good prediction of the added water to the ocean and ultimately of the sea level rise. So on the right, you can see this simulation of the Antarctic ice sheet. This has been done with our code Mali, and the particular Matt Hoffman and Trevor Libram from Los Alamos work on this simulation and on the nice video. And so you can see how the glaciers, the Antarctic ice sheets retreat and over these couple of hundred centuries, and this is under the SSP 8.5 emission scenario, which is what is normally referred to as the business as usual scenario, and so in terms of emission of CO2 and green gases, and so it's and this in this case, like this leads to like I think 8-foot increase of sea level in the next 2 centuries, and which is only due to Antarctic, and then you still have to consider all the other glacier and Greenland. So this one is a particular simulation. I mentioned there is it's under this scenario, so that determines the forcing in terms of snow accumulations and surface melting from the ocean under the ice shelves. But also this is just one particular simulation, and there are a lot of uncertainty, and so in this model. In particular, yes, you have uncertainty in the sliding law, which is what we will focus on today. You have uncertainties in the Kelvin law, the rheology, and of course, as I mentioned before, the major uncertainty, which is the one in the climate forcing. One way to I mean, how do you handle this uncertainty? Well, first of all, you need to do a calibration, and you need to do that anyway before running a forward model. You need to calibrate your model. That's an essential step. And so in this step, you basically try to estimate the unknown or poorly known parameters. For example, at the bed of the ice, you have the basal friction, and that's a parameter that it's a field, and there is no way to measure it directly, so we have to solve an inverse problem. And of course, if you embed this in a Bayesian framework, then not only you have an estimate for a parameter, but you also compute its probability distribution. And then once you have this probability distribution of your parameters, you can sample this distribution and then propagate forward the uncertainty. And in our case, we are interested in uncertainty on the total mass change of the glacier, because it's what directly relates to the sea level rise. And so this is what we are going to do. And all these both the calibration, Bayesian calibration, and uncertainty propagation are extremely challenging from a computational point of view, because we are working with infinite dimensional parameters. Of course, when you discretize them, they are finite dimensional, but they're very high. So you can easily have hundreds of thousands of parameters, and so you need methods to address that, as we will see. And in terms of on the propagation of the uncertainty, we will focus on a multi-fidelity approach to accelerate the computation of the uncertainty propagation. Okay. So now I'm going to present the ice sheet model, the equation, the physics, and also the implementation. While I'm here, I want to give credits to all the developers of Mali, which is our sheet code, in particular Luca Bertagna, Max Carson, Kim Lejoie, Jerry Watkins, and Irina Tesar from Sandia, and Trevor Hilbrand, Matt Hoffman, and Stuart Prince from Los Alamos. So the ice behaves, first approximation, behaves like a very viscous shifting fluid, which is driven by its own gravity. And so if you look at the cartoon on the right, you can see that you have some snow accumulation at the top of, typically at the top of the glacier. The snow becomes compact, it becomes ice, and then it starts flowing downstream due to gravity. And part of it will melt before reaching the ocean, and part of it will go into the ocean, and then will further melt into the ocean because of the warmth that comes from the heat that comes from the ocean, and also it will break off into the ocean and eventually melt. And so we model the velocity equation typically with Stokes equations. And this is a typical Stokes equation for fluids. The main thing is that it's not a Newtonian fluid, it's a shear thinning fluid, so the viscosity is not constant, but depends on a negative power of the deformation tensor. So on the right, you have a simulation where you compute this velocity, and it's the surface velocity in Greenland. It goes from so the blue is a very slow velocity, and the high is up to 4,000 meters per year velocity, and so you might wonder what are the boundary conditions for these equations. And so at the top surface of the ice, you really have a stress-free boundary condition. And the place in the cliff where is the ice in the ocean, you have the back pressure from the ocean. And then probably the most important boundary conditions, what happened between the ice and the bed. And we typically have some sliding boundary condition. Of course, the ice cannot penetrate the bed, and so you have an impenetrability condition. And then the shear stress is in this simplified law, it's really proportional to the velocity. So and with beta is a coefficient of proportionality. If beta is 0, you essentially have free slip, so the ice is free to slide over the bed. And when beta goes to infinity, you essentially have no slip condition. That typically happens where the ice is frozen in the bed. So as I mentioned before, this is very simplified condition. We use this for this analysis, but for example, the video you saw at the beginning for Antarctic simulation was using a more complex and nonlinear boundary condition. And then another important equation is the thickness. So if you think of the ice as a kind of a extruded domain, extruded in vertical direction, the thickness of the ice can be modeled by this equation, which is so h is the thickness, use the velocity, u bar is the vertically average velocity. So you compute the velocity with Stokes, and then you average that along the vertical direction. And then you have some accumulation ablation rate. That, for example, is due to the snow accumulation. If it's no accumulation, will be a positive term. If there is some melting on the surface, then it will be a negative term. And here I'm just giving like an example of a very like a time discretization, how you can couple this with the Stokes problem. And this is what we will use later for the forward propagation. So it's very like first order time discretization. And in this case, we use implicit Euler for the thickness, but then it's coupled explicitly with the Stokes equation. And in fact, you see that for a given thickness, you have a given domain, given the thickness, you solve your Stokes equation, you compute the velocity, and then you use the vertical average of that velocity to advance the thickness to the next time step, and so on. Finally, the last thing I want to say about the model is that we have implemented this in a C++ code. I mean, it's part Fortran, part C++, but the part we are talking about today is mainly C++ part, which is the velocity solver. And then it uses a lot of Trilinos packages. Trilinos is a software library that it's mainly used for linear solvers, nonlinear solvers, and in our case, we also use optimization packages in it, and automatic differentiation package. And Mali relies on the Cocos programming model for performance portability, so it can run efficiently on GPUs. And lately, we have been running it on Frontier. Okay, now I want to move and talk about the ice sheet model calibration. We first consider it as a deterministic approach, like a constraint optimization, and then we kind of see this in a Bayesian framework. So the main contributors for this are Kim Lejoie, Eric Phipps, that they work on in particular on the automated differentiation part. Drew Curry and Dennis Ritzel for the optimization solver, Trevor Gilbert and Steve Price for our climate expert, and they provide also meshes and expertise, and then Georg Stadler from NYU. As I said, we want to do a deterministic inversion. So this is our framework. You want to minimize some functional that is where you have a misfit between the computed velocity and the velocity, observed velocity, typically a velocity that come from satellite observations. And then you have some regularization term that helps with the well-posedness of the inversion. And this functional depends on our parameter P. In our case, we look for the basal friction coefficient, and we parameterize it as the exponent of the parameter P. This simplifies the optimization because beta is a positive term, and so if you take the exponent of P, P can be doesn't need to be bounded, and so it makes the optimization simpler. And then the velocity U depends on the parameter P through our physics model, right? So, for example, if you're using Stokes, then for a given parameter P bounded that determines the bounded sliding north boundary condition, then you can solve the Stokes equation, you get your velocity, and so you can compute this functional. So that's why it's called constraint optimization, because it is constrained by this partial differential equation. The last thing I want to notice the kind of regularization term we are using. So regularization is, as I said, is used to improve have a well-posed problem, but it's where you say what's your prior knowledge. So, for example, if you expect the field to be smooth, then you will add this term where you penalize basically the gradient of this term, and so you will end up with a field that's smoother. This is a simulation that we've done, like in PD constraint optimization for the Greenland ice sheet. So you can see on the left the velocity was computed to match the observed high speed velocity that comes from satellites, and we did that by tuning the basal friction parameter. So this was the parameter we tuned, and in this particular case, our physics model, in addition to the velocity equations, had also a temperature equation. So in this case, as a byproduct, you also you come up with an initial field for temperature field for the ice in the interior of the domain. But yes, so this kind of simulation in this case was like 300,000 parameters, because the basal friction, as you can see, is a field, so it's defined at every point of the grid, and again, the continuous will be an infinite dimensional field. And it was done on Maersk Core computer. This simulation is, I think, 3 or 4 years old, but yes, it's still relevant. And then from now on, we started with a really nice video of Antarctica, then we went to Greenland, and now we go to a smaller glaciers, because it makes things much easier computational wise, especially when you're experimenting with new methods. So now from now on, we focus on Humboldt. Humboldt is one of the biggest glacier in Greenland. And here you see similar calibration. So you have the search speed, the model at high speed, and then this is the model at basal friction. Yeah, I'm sorry, I changed the color scheme with respect to the others picture, but so this is our the parameter, the basal friction, the beta in the equations. Okay, and then so from now on we will focus on this glacier, and now I want to just spend a few minutes to give you a little bit more details about this calibration, in case some of you are interested. So what kind of numerical optimization approach we use? So first of all, we use a reduced-based approach, meaning that we interpret the functional, which is the objective functional j, which is function of the parameter as and the velocity, as a function only of the parameter p by solving the constraint that gives you the velocity as a function of the parameters. So this basically in the reduced space, this optimization is no longer constrained. And then we use a trust region method, which is implemented in the in ROL, which is a rapid optimization finite library, which is also part of Trinos. And you use you solve this using truncated conjugate gradient method. In order so if you're not aware of how trust region method works, essentially you want to minimize a high dimensional functional, and you focus on a point, and you create a quadratic approximation of that functional in a point, and then you have a region, the so-called trust region, where you trust that quadratic approximation, and then you find the minimum of that quadratic function, and that will be your next guess for your parameter. So this is very kind of high-level description, not precise at all. And in order to apply this method, we'll have to compute reduced gradient and the reduced Hessian of the functional, and we do this with both automatic differentiation and solving adjoints. Here it's another slide that tells you a little bit more how this different component works. So essentially, the numerical optimization solver wants you to compute the Jacobian, the objective functional j for a given parameter. It's reduced gradient, and then solve this quadratic subproblem to compute this quadratic approximation. And so when you want to solve the functional, you have to solve a nonlinear problem. So you have a linear solves, and then you have around a Newton loop for solve it. To compute the reduced gradient, you need to solve an additional adjoint equation, which is linear. And then in order to solve the quadratic subproblem, you really want to find the to solve the system. The problem is that the Hessian of the functional is dense, and we're talking, as I said, about hundreds of thousands of dimensions. So you definitely cannot compute it. So what you do, you solve this with a Krylov approach, where you compute the math vector product, and so it's a matrix-free approach. And then for evaluating this math product between the Hessian and the direction, you have to solve two adjoint systems. So this is just to give you an idea. And so for example, we tried it on the Humboldt Glacier with no particular optimization, and we'll end up solving like 3,800 linear system for one optimization. And let me see how I'm doing with time. Yeah, very briefly, there are ways to improve this approach. And in particular, one thing that's typically used is that so you determine the reduced gradient is basically the actual gradient is determined by the dot product that you use to define the gradient. And if instead of using the typical Euclidean product, you use a product that is based on the mass matrix, in terms when you have, like, for example, like fine-time discretization, then you typically get a much better result, especially when you're working on variance structure meshes, because the mass matrix incorporate information about the matrix, and so you get a much better result. And the other thing we found to be very useful was to precondition this Hessian with BFGS approach. So I hope you're familiar with the BFGS, but it's a low-rank approximation of the Hessian, and it's important, if you do this, to initialize it with the Hessian of the regularization term. So if you do all this optimization, you can see that you go from solving like, so this is the history of the reducing the functional, and you go basically from having to solve like 10,000 linear system to less than 2,000, and so which is it's improved both the robustness of the method, and of course it's more efficient. And this just one last point, mentioning that no matter whether we use this vanilla approach or the improved approach, of course the improved approach is much faster, but if you look at where we spend time, it seems that we spend most of the time evaluating these multi-fidelity products, so in particular in the assembly time, to assemble the derivatives with automatic differentiation. And so this is something we were going to work on to improve the speed of this approach. But we think that these are done on CPUs. As soon as we move to GPUs, we expect to get a big advantage from this. Just a comment. So the forward simulation ran already on GPUs and efficient there, but we haven't ported the inverse problem on GPUs yet. We are close to do that anyway. Okay, now we've seen how you do this deterministic inversion and some details about the performance. Now we move towards to the Bayesian calibration, Bayesian inference approach. And here the main contribution of this part is Tucker Hartland from Lawrence Livermore and Kim Lijoie and Georg Stadler. So again, I hope you are familiar with Bayesian inference. Here it's not, I'm not really trying to tell you what it is. I'm just recalling and basically get you familiar with the notation. But so the idea is this, to use the bias rule. So we have a and we want to compute the posterior distribution, which is the probability distribution of x, which is our parameter given the data, and this is equal to the what's called the likelihood. So the probability distribution, the probability that you're given the data, I mean of the data given your parameter x, and the probability of the parameter of your parameter, which is the prior. And so so we are using this rule, and the typical approach where we model, where we assume that the data is given by our physical model. So with M is the parameter to observation map. So you have a parameter, you solve your Stokes for you compute the velocity, and then you compute the quantity of interest that the quantity of interest, and then in our case could be like the surface velocity, and then you match it with the data, which is in our case observed surface velocity, and then we assume that you can reproduce the data up to some noise that we assume to be Gaussian and with zero mean, and then the likelihood function, we also assume it's Gaussian, and it's given by this expression, and where M is the where again you basically it's weighed by the misfit between the model and the data. And then in terms of the prior distribution, we typically assume the prior to be again Gaussian, and given by this form where sigma is prior is the covariance of the prior, and then given this quantity, we can compute the posterior, and we see that it's proportional to this exponential, and again you see the two terms. The first term is related to the misfit, and the second term is this prior on the parameter. The map M is non-linear in our case, and so the posterior won't be Gaussian even if the prior is Gaussian. So this it's basically you can solve this with this inference problem, like solved with Monte Carlo method, in particular Marco Monte Carlo. But for the kind of dimension we are looking at, this is completely infeasible. And so here we are using an approximation that was proposed by the Omar Gatta's group and other people before, but was introduced in the ASH model by the Omar Gatta's group, and I'm referring in particular to this paper, even that there are a few papers where they developed this. And really all the framework here about the Bayesian inferences is follows that approach in that paper. And so we do have this Gaussian approximation. Essentially, we perform a quadratic approximation of this term centered at the map point, which is the maximum posterior point. And you can see that which will be the mean. And you can see that this point is really just the minimum of this expression, which has the misfit term and the regulation terms. Now, if you compare this to the deterministic approach I presented before, this is really can be seen as our objective function of J. So there was a first term where you weigh the misfit between the velocity and the model velocity and the velocity, which can be this term if you choose depending how you choose the covariance matrix sigma noise. And then the regularization as well is really this prior term is really what we call before regularization. And again, if you choose the covariance to be like the properly, you can reproduce that problem. Now, because we want the variance of the prior to be finite, we cannot really use gradient square regularization, but we need something a little bit stronger. In particular, we are using a Laplacian square regularization. And so this is what we are doing. And I don't want to go through the details, but you can express this prior with you can express this prior given the finite element mass matrix and a stiffness like matrix, and then you can sample from this distribution by starting from your parameter. Beta 0 in our case is typically 0, and then you have L, which is a Cholesky factorization of the or a square root of your covariance matrix. And so and N is a vector of IDD variables that are that follow the Gaussian the normal distribution. Okay, so if we can sample from this prior using this method, and in our case, if we do that, you can get some samples of that look they look like this. So these are I'm showing here three samples from the distribution, prior distribution, and then the variance of that prior, which you see that's fairly flat, which is kind of what we want, because we want the prior not to be too informative. And then again, you can then you can compute the posterior approximation given this quadratic approximation that we did, the Gaussian approximation. The problem here is still in the high dimensional parameter space, so you need to do some computational tricks to try to come up with some low rank approximation of it. Again, it's described in the paper that I mentioned before. And if you do this, you can come up with low rank approximation of the posterior covariance. And here I'm showing the eigenvalue spectrum of the covariance. And you can not quite of the covariance, what's called the prior preconditionation, but it's representative of the actual covariance. And you can see how you need to you can see the spectrum. In order to have a good approximation, we need to keep all the eigenvalue and eigenmode that are until the eigenvalues are well below 1. And so in this case, for example, we have to probably keep about 800, 1,000 eigenvalues. So in this case, this Humboldt Glacier, the size of the problem is about, I think, 10,000. And so you see, here we're doing an order of magnitude reduction in the dimensionality of the problem, but we still have to handle a very high dimensionality. And so these are the eigenvectors, some of the first, second, and 10th eigenvector. You can see that of this precondition relation. And then if you sample from this posterior distribution, you compute these posterior samples. These are the mean free, so we didn't add yet the mean, which is in our case is the map point, which is basically the parameter that we obtain from the deterministic optimization. And so one interesting thing to notice is that the bottom right is the variance of this posterior, which is we can see that it's informed by the problem. In fact, you see that the variance is much smaller close to the outlet of the glacier. So the glacier essentially is the ice is flowing northwest, and this here is the outlet. And so parts of the glacier that are close to the outlet are way. I mean, the basal friction here it's way more have a way bigger impact on the ice flow than the basal friction here. That's why the variance is informed much more in this place, and the problem is informed much more in close to the outlet, and so the variance there it's smaller. And then finally, this is when we add that to the map point, then we get the actual samples from the posterior. So the first one is the map point coming from the deterministic optimization, and the other ones are perturbation that are obtained with this approach. Okay, so now the last part of the talk is, and it's as I mentioned, it's the novel part. It's about forward propagation. And in this case, John Jackman is the lead of this effort, and also Tom Siddle, Tucker Hartland, and Trevor Hilbrand with this work. Well, first of all, the idea now is to propagate the uncertainty. So we have now a way to sample this posterior distribution. There is no explicit form of this probability distribution, but we can sample it. And now the idea is that we sample the distribution, we get our parameter, we solve our model forward in time for like 100 years forward in time, and we compute the mass change of the glacier. The mass change is our quantity of interest. And so, you can use a Monte Carlo method, right? So you can sample this probability distribution hundreds of thousands of times, and you get and then you get the mean on your total mass change of the glacier, and you can also compute the variance if you want, the total mass change, and in that way you characterize what's your quantity of interest and some statistics on the quantity of interest. The problem with the Monte Carlo it's very slow, and so the multi-fidelity approach helps us in accelerating this process. So the idea I'll try to start with the concept of multi-level Monte Carlo method. So the idea is that you have different models of different fidelities, and in a second I'll describe them. But the idea is that the F0 is the high fidelity model, so it's very accurate, it's what we trust, but it's also very expensive. And then we have other models that are lower fidelity, so they're cheaper, but their accuracy is not great. And so the idea is if you can combine them to accelerate the process or reduce the error on the expected quantity. So we are looking at the mean of this model. So again, think of a total mass change in our case. So we want to look at to see what the mean of the total mass change, and you can write this as the sum of the mean of F1 plus the mean of F0 minus F1. Now, if you do if you want to estimate it, so you use the typically mean estimator, and so which is essentially an average over what you use over a set of samples, and so you write this as this sum. Now to see how well you're doing, you look at the variance of this estimator. It says if it has a large variance, then it means you're not doing a good job with your estimate. But you want it to have a small variance, so you know that the value that you give is accurate. And so if you compute the variance and you're assuming these sample sets are disjoint, then you can easily write it as 1 over n1 times the variance of the F1 model, and plus 1 over n0 times the variance of the difference of the model. Now, the trick here is that the F1 is cheap compared to 0. And so you can evaluate it, sample it a lot of times. So N1 can be very big. And so you can reduce this term by sampling this cheap model many times. And then if you look at the second term, if the two models are well correlated, then the variance of the 0 and the minus 1 is much smaller than the variance of F0. And so this term is small as well. So this is the idea. You use this for a model, and you can accelerate. And of course, you can think that if you know the cost of F0 and F1, you can find some optimal values of N1 and N0 to minimize the variance for a given fixed cost. And that's the main idea. Now we're working on a generalization of the multi-fidelity Monte Carlo, and I'm not going into the detail. But the idea is that you can improve on the Monte Carlo by doing two things. One is that selecting what models you use. So say we have, I don't know, 10 models, and they say, okay, pick 3 of these models, and the best 3 of this model that allow getting the smaller error on smaller variance. And so you can select those. And then the other thing you can do to come out with an optimal strategy is the sample sets. How do you define those sample sets? And so again, I don't want to go into the detail. We use a code that written by John Jackman, and you can find it online, and it says also have a very good documentation. So if you're interested in this, that's definitely a good resource. And so these are kind of the hierarchy of physical model physics models that we have, and so they are all approximation of the Stokes model, and they're all based on the fact that these ice sheets are very shallow, so you can do some approximation, and I'm not going much into detail, but so we are considering in particular what's called the monolayer high order model, which is essentially you start from a 3D model, and then you do you kind of interpret it by writing. You come up with an ansatz for your trial function and test function. They're basically given by the average of the vertical average velocity plus deformation terms along the vertical direction, which is a fixed profile. And then you have the shallow shock model where you disregard these terms, so you only assume that the average is constant in the vertical direction, and you come up with the shallowest approximation. Shallowest approximation is a truly 2D PD problem, and the monolayer can be reformulated as a two-dimensional PD. So we have basically two models with different physics. And then we solve them on different meshes. And so here we particularly consider 4 different meshes. And you can see here, I think the finest, and on the back, you see the coarsest one. And here, for example, you can see the evolution in terms of the mass change, in terms of gigatons for a particular sample with changing the mesh. And again, just a couple of caveats about the approximation that we did when you do this propagation study. So first of all, we assume that the ice cannot really the ice front cannot move, so the geometry is fixed. The other thing is that instead of using the Mali code I presented before, for this problem we implemented these models in a prototype code in Phoenix. So these are kind of again plots of the mass change in time as a function of time. This is the year 2010. It starts from 2007 and goes up to 2100. And in the first, on the left, you're using the shallow shape approximation, and on the right, the mole approximation, which is the higher fidelity model. And you can see this as a function of these different samples. And then this you can see here. You can see the so we consider in total 13 models. And here I'm presenting for this study. Here I'm presenting the correlation between 6 of these models, the one that were most promising, most useful for these multi-fidelity strategies. And so you can see the correlation. So for example, in this one you have the high order model with 1 kilometer measure resolution, and then also we chose the time step. In this case, we are using a very fine time step, 9 days. In this case, we are using same resolution, but with a larger time step, 36 days. And then the other ones are the shallow ice approximation on different meshes: 1 kilometer resolution, 1.5 kilometer resolution, 2 kilometer resolution, 3 kilometer resolution, and with the time step of 1 year. And so you can see the correlation is fairly high. You need correlation to be high, like above like 0.9.5 or so, otherwise this method won't be very successful. And this correlation is based on 30 samples. So we took 30 samples of the basal friction, and we ran it forward in time for each of these 13 models, and then based on that we come up with a sampling strategy. And this is the cost of the models. These 6 models. So of course the most expensive, the high fidelity one, and then you see the relative cost of the other. And here is the result. So we try to minimize not only the mean of our quantity of interest, but also the variance with this multi-fidelity approach. And here is basically here we are the projection variance reduction on the mean on the left and on the variance on the right. So essentially what it means is that if you use this multi-fidelity approach compared to the Monte Carlo approach, we will get a variance that is 25 times smaller. Or equivalently, if you want to get the same variance with Monte Carlo, you would have to have 25 times the number of samples that we use. And then in the middle, you see the percentage of cost of the model. So we sampled the high fidelity model 2 times, the middle fidelity model 353 times, and the low fidelity model 10,000 of times. And combination, and you can see the percentage of the cost of this model. And with this, we ended up with computed mean, which is of minus 639 gigatons, and a standard deviation of 17.7. So this compared to the approach I present, the simplified approach at the beginning, and the classic multi-fidelity method, multi-fidelity Monte Carlo method, here we are able to minimize not only the variance on the mean, but also the variance on the variance. So we can get a value of the standard deviation that we trust, not just the mean. So yes, this is all I have for you today. And so I think demonstrated a workflow to compute the mean and variance of the glacier, starting from the Bayesian calibration, and then sampling from the posterior distribution, and then using this multi-fidelity approach for the forward propagation. In this model, we also have good correlation between the models. when we start considering putting more physics, for example, carving more non-linearities, we might not see such good correlation. So this is something we're going to explore. And so we demonstrated that this work with a real glacier example. And yeah, so another thing that I'm interested in, and it's something we're working on now, is to use machine learning to create surrogates. So in addition to this model like shell-sharp approximation, the monolayer Hurd approximation, where you could have some model that's used using machine learning, and then you can use that model in this multi-fidelity framework. So that's something I'm interested in, and I'm working on now. So that's all, and thanks for your attention.
Are there any questions?
Hello. Yeah, anybody has questions? Thank you very much, Mauro. So I just wanted to any questions?
Yeah, I have a question.
Thank you. Go ahead.
Mauro, this is Trevor. I was
Sure.
wondering, on one of your final slides on the multi-fidelity, you showed, I think, 2 samples of the high fidelity and 10,000 samples of the low fidelity. I was wondering how you determine the trade-off between the number of samples needed and the value. Yeah. So the purple versus the
so it is really this multi-fidelity approach, essentially to like you really as I said, so you really want to minimize the mean and the variance, right? The variance on the mean and on your quantity of interest, say. And so in order to minimize it, you consider a lot of different models, and so all you say to them, to this method, is pick 3 models out of the 13, and then this is what it comes out with, trying to minimize that. I mean, if you want more detail about the optimization, I can probably, I don't know if John is online, but that's it. Yes, it's really the tool that really look at all possible combination and comes out with the one that minimizes the variance. And this is done, as I said, on a pilot study. So you have a pilot study of 30 samples for each model, and then looking at that and at the correlations and the cost of the model, you come out with a sample strategy based on that. Does it make sense?
Yeah. So do you have a sort of...
Our input was only really pick 3 models out of these 13, and that's
yeah. But I'm wondering why it doesn't partition the cost more evenly between the 3 choices here. Like, why not use a third of the target cost as the high fidelity model and a third of the lower fidelity model?
Well, because that won't be the optimal solution. Won't be the solution that minimizes the variance.
Okay.
I think it's not. I mean, I don't know if there is a more intuitive explanation for your question.
But it goes back to this slide 35, table on slide 35 there, and that's the...
Definitely related to the correlation between the model and the cost of each model, right? So you want so for a fixed cost, you want to minimize the variance on your quantity of interest, and so and that's how you pick the models and decide how much to sample each model to try to minimize that. So I think that if you didn't know anything, I think it would make sense to probably repartition the cost, as you said, like, but that's not the optimal solution. You can do better than that.
Yeah. Okay. Thank you.
Sure.
Thank you, Mauro. Thank you, Trevor. Any other question?
Hi. I have a little questions. In one of your earlier slides on calibrations, some of the parameters changed by a factor of 10 to the fourth. Do you have a physical explanation of why that would be so?
Oh, you're talking about the solution. Okay, so like you're talking about the actual parameters, or
Yeah, yeah.
oh, this one. So it's I mean, this is essentially if so when you have a free sleep, the basal friction is basically close to zero. So you can easily have quantities that are like 10 to the minus 1 or even less than that. And that happens, for example, you can see here where you are like in this big ice stream, and when we are a film of water in the bed, and so you can have that. And on the other hand, when you are in places where the ice is frozen, you basically the ice doesn't move. So 10 to the 3 is basically this is almost a no-sleep condition. So both of that are physically meaningful, and so that's what we get. Of course, if you increase the regularization, then you will have a smaller range, but we think this is realistic or reasonable anyway outcome. Am I answering your question?
Yeah, kind of. How do you say, why do you say it's realistic? Well, what's your physical guide there?
Well, again, we know that there are places in the ice sheets where there is essentially the ice is basically freely sliding, and there is where you expect the basal friction to be very low. And then we know there are places where the ice is frozen, and so basically there is no sleep at all, and then we expect that to be very high. So that's how I'm motivating it. The exact values we don't know, and the only thing you could do is really validate this with forward run and do some and validate that with observation. So like do some kind of in-cast study and see how this behave, but it can the validation of this inversion is they're not simple at all, because there are tons of other things that play a role, and not just so here we isolated one parameter, but there are several, but yeah, so that's how we try to validate this model.
I have a follow-up question.
Sure.
So the later part of your talk, you talked about a much smaller domain, right? How do you expect the procedure to upscale to a much larger one?
Yeah, so in terms of the Bayesian inference, I think all the tools we use we can parallelize them, and so it is scalable. Of course, it would require more computational resources, but it will be close to linear kind of cost increasing if you increase the number of dimension of the degrees of the number of degrees of freedom. So for and similarly for I think for the multi-fidelity approach, of course the problem is that now when you run, like for example here we run 10,000 simulation, then each of those is you can parallelize. So say you consider full Greenland, you can parallelize that. So in terms of hour, it's you can be basically the same. But then you're using, instead of one core, you're using like 10,000 cores or 10,000 cores. So the cost it scales. Again, I expect these things to scale linearly. But yeah, so it's if your problem is 50 times bigger, then you at least you have to have use 50 times more resources. Yes. But yeah, I think all this method can scale. So. And as you know, I mean, yeah.
It's the expensive that will be probably the bottleneck.
What's the bottleneck?
Probably the expensive solver, the accurate solver, right?
Yes. Yes. So in all of these, it's really it's a function of the cost of your forward solved, or for the inference, the cost of your Stokes problem or whatever approximation you're using. So that's really that's kind of what dominating the full cost. And of course, so okay, so maybe another thing that's relevant to your question is if you look at these plot here. So where was it? I can find it. So something that might change is that when you do this Bayesian inference and you look at the low rank approximation of your prior preconditioned Esha, what can happen is that instead of having to using, I don't know, 800 eigenvalues, you have to use more. From what you've seen from the literature, in particular, the work that Margatta's group, in particular, Tommy Isaac and Vivek Style and Noemi Petra did, these are similar also when you consider a full sheet. So it would be maybe instead of 600, the crossing would be at 1,000. So that can increase, but it's not gonna be like 10 times more. It will be probably a little bit larger. That's what we expect at least. So this is something that determines the effective dimensionality. And if this increases for larger problem, then it's an additional cost. But again, as I said, we don't expect this to change much. It could be maybe twice as much, 3 times as much, but not like 50 times as much as you go from a glacier to a full scale ice sheet. And we've seen this in a couple of worlds, so that's the case. So you're not too worried about that.
Thank you.
Okay,
Nice
yeah,
talk.
thank you, Mauro. Thank you, Mohammed. So any other questions?
Maybe one more. We go back to the multi-fidelity results.
Yes.
It looked like you sampled out of 3 models, but I thought you had more models. Did your method choose to only sample 3? Did you choose to limit 3?
That's your it's like what you say hyperparameter nowadays. So that's something that you decide. So how many models you want to? So you have like in this case we have 13 original models, and then what we ask is in this case is to pick the best 3 models. So the 3 models that are best for minimizing the variance. And so that's why we have also results with 2 and 4, for example. So that's a choice. But you start from these 13 models, so they're all considered, and then you pick the one that I mean the method picks the one that makes the most that are optimal. Is that clear?
Does it very much? The results change much if you do 4 or 2 instead of 3?
I actually, so I've seen the 4 one doesn't actually change much, and not 100%. I don't remember. I don't think it changed dramatically. So not, but it changed a bit. Yeah. I don't know. Is John Jake Manario still online? I can actually.
Yeah.
Okay.
Yeah, I can actually I might be able to, if you have 1 minute, I might be able to look it up very, very quickly. So for So, okay, no, okay, so for 2, the variance reduction was 19. So yeah, it was with 2, you have the variance reduction was 19 and 15. So was significantly less. So with 3 you have 35, and with 4 and with 2 you have 20, almost 20. And then for this is for the variance, here with 3 you have 25, and so with 2 you have only 14. So yeah, yeah. So if you use 2 with respect to 3, it makes a difference. Sorry, this is kind of very fresh results, so I'm still not still have to process some of them, and then yeah, and John Jackman made these solutions. Okay,
Thank you very much.
sure.